Good morning, everyone. Okay, let's get today's lecture started. Any questions from yesterday's class?
Yesterday, when we showed that the protein molecule BPTI, so in that NMR spectrum, there was a peak in the which has negative chemical.
The question that is being raised right now is that resonances that arise from proteins, and you do see some chemical shifts that are negative. So this raises curiosity. This is a very good observation. Generally, the region from here to here comes due to methyl protons, and methyl protons are present in alanine, valine, leucine, and isoleucine. And generally, how a protein folds is to have tight packing in the core driven by hydrophobic interactions. And hydrophobic interactions are significantly driven by methyl groups and aromatic rings. When these methyl groups end up being buried in such a core with quite a number of different atoms that are present in it, the chemical shifts could get much more de-shielded. So anything that goes downfield is generally regarded as shielded. Anything that goes upfield is regarded as de-shielded. Similar to the fact that the nitrogen proton HSQC serves as a fingerprint, the methyl proton resonances also serve to say whether a protein is folded or not. When a protein is folded, one of the characteristics is to see methyl peaks close to 0 ppm or even upfield of 0 ppm. So that's a very good question. So ring current effects that are due to the aromatic rings, many things play a role to cause chemical shifts to be perturbed. But as you rightly pointed out, the resonances that appear in the upfield region of the proton spectrum are a clear indicator of a folded state of a protein. So you can get a lot of information just from proton 1D NMR. For instance, the folded state would also have a good dispersion of the amino protons, okay, and the methyl groups that are being present here. Otherwise, what's going to happen is that you're going to have heaps of resonances. You won't have, you'll have some here also, but you're not going to have nicely resolved peaks as you see right now. You see nicely resolved peaks, isn't it? I'll try to get the assignments for this so that we can try to put it in context on what we are seeing here. The same aspect would be highlighted here as well. You would see that these are the protons that are one of the most upfield shifted. So these are potentially in the core of the protein. Any other questions from last class?
Sir, yesterday you told is proline doesn't have NH protein, so it's not possible to see proline in HSQC. Nitrogen had 1500 HSQC, but sometimes there are also some other amino acids we can't see on HSQC. So, like I think in ubiquitin that G54 is sometimes it's difficult to see on HSQC.
Yeah, those are other reasons. We know that the line length is dependent upon R2, and R2 is dependent upon R2 intrinsic and REX. That is happening because the line width is getting broadened due to a factor called exchange, chemical exchange or conformational exchange, due to which the lines are much more broader. Since the area under the curve has to be constant across the resonances, you would end up having, if you have a broad line, the intensity reduces quite a bit. Okay? You're taking a specific example from ubiquitin, and then you're trying to highlight that you don't end up seeing it. That could be due to other reasons. But I'm talking about a chemical reason that definitely any proline that you end up looking at, you'll never be able to see it from HSQC. Okay? The REX could be different. That depends upon the protein's conformational landscape, how flexible it is, how dynamic it is. We won't deal with these aspects in the course, but if you see that the chemical shift difference between the states, let's assume that the protein ends up sampling two different states, A and B. It could be folded and unfolded states, just for an example. And it'll have a forward rate, it'll have a backward rate of conversion. So the sum of the forward and backward rate constant is called KEX, okay, exchange rate constant. In the case that you have the chemical shift difference match very close to the exchange rate constant, of course, with the dimensions matching properly, this should be in hertz and this should be in second inverse, then you would see a resonance broadening that happens. So some resonances broaden due to other reasons as well. And that's what you are trying to highlight. And many times, many proteins have such unique amino acids, which will cause such a change. So an absence of a peak could be quite interesting beyond the scope of just the chemical entity that's being present. Every amino acid should give you an NH. Now, if an NH is missing, that's a very important aspect to go behind and understand why is that happening.
So yesterday there was a question about what is that big line at 4.7 ppm.
So this is the water resonance that's present in your buffer. Water does not have a carbon attached to it or a nitrogen attached to it. Generally, these experiments are done at 90 to 10% H2O to D2O, or 95% to 5% H2O to D2O. We add D2O for field frequency locking, which is an important step when you set up the NMR experiment. Since there is no carbon attached, it will not give a specific signal. Then you may ask, why is it coming at all? That's because when you execute the pulse program, there'll be some amount of relaxation that happens before the last 90-degree pulse. So after the water relaxes, you'll still be able to see it. We end up doing some techniques to suppress water, as you have effectively suppressed here, but not always it happens. One other important aspect that comes up here is that we have to prepare our samples in water so as to make sure that the NHs are indeed visible. We end up preparing a sample in 100% D2O, all the NHs will become NDs and you might not be able to see it. Sometimes people do it for other reasons, but quite commonly when the people prepare the protein sample for the first time, they're prepared in the H2O solvent in order to make sure the NH peaks are visible.
Is there any reference you're using to qualify the shift of the D2O?
Yes, good question again. The question that is being raised is that, are we using a chemical shift standard to determine the chemical shifts precisely? In small organic molecules, we generally end up using a molecule called tetramethylsilane, which is referenced to 0 ppm. The problem with tetramethylsilane is that it's a highly hydrophobic molecule, therefore will not be soluble in water-based aqueous solvents. Therefore, you cannot use this. So we tend to have a modification in tetramethylsilane, where one of the methyl groups, instead of being CH3s, will have a CH2 sulfonate. SO3, I don't know how many minus it is. So basically a sulfonate salt or a propanoate salt, CH2COO minus. Okay. These are standards called TSP. I forget the full form of TSP and DSS. So there are other internal standards that are there that will help you reference the chemical shift for proton and carbon using these internal standards. Else the chemical shift, every time you measure it, there'll be some small deviations that come. With the pH changes, there'll be changes that come. We just said chemical shifts are very sensitive to structural changes. And structural changes change upon many different factors. One of the main factors is also buffer. If you prepare a buffer in a certain pH, you might actually find a folded state. For some proteins, if you prepare it in a different pH, you will either unfold them or they will start aggregating. So the other problems come up. So since we are setting up a thermodynamic experiment, meaning that at equilibrium we are studying, the buffer conditions have to be clearly mentioned at what pH is being done, what are the concentrations of different salts that are being used. In addition, the temperature at which the experiment is done should also be explicitly mentioned. Because as you change the temperature, there'll be changes that come up into the protein structure, which will once again affect chemical shifts. Because we know that as we keep increasing temperature, proteins tend to unfold. When unfolding happens, secondary structure and tertiary structure are lost. The chemical shifts change. So everything has to be carefully documented in order to make sure the data is properly provided to the community. Okay, so in that aspect, you would also add DSS as an internal standard to ensure. The cases where people neither use DSS, TSP, internal or external, is to use the water resonance as a reference to calibrate chemical shift. And water chemical shift is also very sensitive to temperature. As you keep changing temperature, the equilibrium constant changes a little bit here and there. Therefore, there are quite a bit of hydrogen bonding changes that come up as you change the temperature for water. Due to which the chemical shift also migrates quite a bit. So this is a last resort that people would end up doing, where they use the solvent resonance to calibrate their chemical shift.
How do we align the X and Y axis? Let's say you took a nitrogen spectrum, you took a hydrogen spectrum, you have to make a 2D plot. So how do you know, like, how do you scale them and like?
The question that's being asked right now is that you get a proton spectrum, you get a 13C spectrum, how do you align them? We will discuss this today, but I think there is a small misconception in your understanding. We don't acquire carbon and proton separately to put them together in some way. We'll get both simultaneously. You will see that. Okay, we'll have the modulation of the carbon chemical shift on the proton resonance. We'll somehow correlate proton shifts to carbon shifts. And then when you just do a Fourier transformation, two-dimensional Fourier transformation, you'll get it.
We acquire them on separate channels, right?
No, we did not. We'll acquire only on proton. We will see how that goes. That is why we don't acquire them on separate channels. That's why a proton channel, wherever the FID is acquired, will be called the direct channel. Wherever you acquire the carbon or any other heteronuclei indirectly will be called the indirect channel. We'll see how we execute it today. But excellent questions. Any other questions?
Sir, when the salt concentration is very high in the buffer, it is very difficult to suppress water. Why is it so, sir?
This goes back to what is called, it's the hardware related phenomenon. The probe, which is where you have the transmitter receiver for all your signals, is sensitive. There's a filling factor that comes in. The filling factor is very sensitive to any changes of buffer that you have. Remember, you're applying radio frequency pulses. When you are applying pulses, how are you sure that the pulses are only transferred to the sample and do not get wasted as heat? This is one of the steps that we do where when we start the instrument or the experiment, you do a step called tuning and matching, which ensures the heat is minimized when you reasonably tune and match the probe. But as you start increasing the salt concentration, it becomes more and more difficult for the probe to get reasonably tuned and matched. And therefore, when the probe is not reasonably tuned and matched, your pulse widths, whichever previously was 10 microseconds for a 90-degree pulse, might start to go to something like 13 microseconds. I'm just giving an idea. When this starts happening, when the 90 degrees, 13 microseconds, here 180 degrees becomes something like 26 microseconds, which is really long. There's something called off-resonance effects that come. A lot of other factors start to come in. Okay, so due to which, when the moment you have high salt, there is something called eddy currents, which will result in wastage of heat. And since that happens, you will not be able to set up your experiment the most optimal way. This is generally combated when people use a room temperature probe. Since we are working in biomolecular labs, we use something called a cryogenic probe or a cold probe, which is super sensitive to salt concentration. So the long and short answer for your question, why when you have high salt, it's difficult to suppress water. Why does water signal come up too much why you can't effectively suppress? Is because as you start increasing the salt concentration, the effective tune match is almost lost, and therefore other things start to happen there. Okay. I'm not trying to say this is the best explanation. We will see after we see the hardware. There are way too many concepts to cover in NMR. I'm trying to make sure we reach the two-dimensional part and the protein part at least a little bit, and at the same time touch the hardware and practical aspects of it. So I am not saying I'm giving you all the information here. I'm trying to give you the most critical information so that you can patch up the remaining. But these are wonderful questions. Keep the questions flowing. The question that is being raised, how would we quantify signal to noise ratio in a 2D experiment? Let's first ask, how do we quantify signal to noise ratio in a 1D? Okay, so you have a resonance like this. What you try to do is to first pick the peak. Okay, maybe there are two peaks here. There's a shoulder. And then you find the intensity of it, which is a readout from what you get after Fourier transformation. And these are also intensities, isn't it? You can take the average of it, which should average close to 0, indicating that there is no offset. You would end up getting a standard deviation. If the noise is more, you'll get a high standard deviation. If the noise is less, you get a lesser standard deviation. There are different definitions of how people define noise. One of the definitions I tend to follow is that the signal to noise will be defined as the intensity divided by 2.5 times of the standard deviation. The 2.5 times come due to a different reason, statistical reason of why it has to be 2.5. Some people just like to do I over sigma without taking the 2.5. So I tend to take I over 2.5 sigma, and if that is greater than 3, I would call it a signal. So this is from the 1D spectrum. The 2D is not very different. When you have a 2D spectrum, let's assume this is where your resonance is. You would once again pick a peak that takes care of the X-channel chemical shift and the proton chemical shift. So you will get an intensity for that peak, right? Instead of measuring noise in a 1D fashion, you will measure noise in a 2D part. You will draw different boxes and check what is the standard deviation in each of the box. They will more or less match. Depending upon the area, things will change, but there will be reference to the area that you draw. If you draw a bigger box, more points will be sampled in, isn't it? You draw a small box to get noise, less points will be sampled. But at the end of it, if the noise is similar across all parts of the spectrum, you get a similar standard deviation. So basically what I'm trying to say, you can measure noise here, or noise from here to here. You would still get a very similar RMS, which is standard deviation. Similarly, in a 2D, you will get the intensity of the peak and you will draw some rectangular boxes of reasonable ppm widths in it so that you can measure noise for a larger part. So for every peak that is being present, you pick the intensity, get the RMS and do 2.5 times the standard deviation to get the signal to noise ratio. Make sense? Good question again. Other questions? This is the first time when I'm teaching NMR course where the first 20 minutes is gone in questions. This is the most effective way of learning. Learning cannot happen only when I give lectures. Learning can only happen when people ask questions. I'm so happy that we have had 6 or 7 questions. Although they are not directly pertinent to what I wanted to teach, but these are very important aspects to understand other things. So I'm happy that you guys are asking questions. So feel free to ask. Now let's go back to today's lecture and understanding how 2D NMR comes. Okay. Before going to how 2D NMR comes, let's rewind a little bit and ask how did 1D NMR work out? I know we keep going back and forth. The reason why we keep going back and forth is because then we will iron out so many concepts that we learned. We said that if the trace of the density matrix to the operator that you're trying to measure, if it comes out to have an oscillation, then when a one-dimensional Fourier transform is done, 1DFT, the single dimension here is the t variable dimension, right? What do you end up getting? You get a delta function at omega I minus omega. Of course, there is a component of relaxation. Density matrix formalism, we will not invoke it, which ends up just coming as a convolution as that absorptive and dispersive peaks. Okay, u omega, u plus I v omega. We had done that before, right? U omega plus I v omega, where this is the absorptive part and this is the dispersive part. So this is what gives the Lorentzian line shape for NMR signals. So therefore, you guys are able to accept that if the density matrix has a certain frequency, that can be picked up after you do Fourier transformation. Right? Without going to the pulse program, let me ask from the density matrix perspective, what should be the density matrix to get a 2D NMR spectrum? If we understand this, then all that we have to do is to generate the density matrix. Right? So first, let's ask what density matrix will give me 2D. Fair question to ask? Okay. We just said you have something like this, you will get a Dirac delta function at capital omega I. Right? Now, somehow if you're able to also generate something like omega s times t, if you end up Fourier transforming, you're going to get the resonance at omega I plus omega s. Because you have a single time variable, if you do a Fourier transformation only with respect to t, you're going to get the sum of the chemical shifts. This is not what we want. We want a chemical shift, which is a nice convolution across the 2 dimensions, where it reports on carbon separately and proton separately. This is sum of carbon and proton. We do not want this. Correct? So the only change that we do to this is to have 2 time variables and do a Fourier transformation, not just with 1 dimension, but across 2 dimensions. Okay, how can you imagine this? You can imagine this as 2 separate resonances that come up, which are convoluted with one another. Basically, T1 and T2 are 2 time variables, not single time variable. Previously, you had a single time variable while you're acquiring the signal. Here, let's assume you have the ability to have 2 time variables and you're varying 2 times, 2 of the different time domain signals. Then if you Fourier transform them separately, they'll give a signal, and basically anything a multiplication in time domain will be a convolution in the frequency domain. Right? Anything that's a multiplication in the time domain is a convolution in the frequency domain. What is convolution? Take a point by point multiplication for each one of them. Okay, I see about 50% people not following. Let me repeat it again. Are you guys able to accept the fact that the density matrix, if it is of this form, and if I do a Fourier transformation with respect to just the T2 domain, I'm going to get a signal at omega I minus omega 2? Do you guys agree on that? If I only do a Fourier transform, assume this does not exist. I have this as a density matrix. I do a Fourier transformation with respect to T1. Then I'll get a delta function at omega s minus omega 1. Why omega 1? Because I'm using T1. Why omega 2? Because I'm using T2. Right? Separately, you guys are able to understand how a signal comes when that is the density matrix. Right? But somehow, if I generate a density matrix, which is a product of these two oscillations, if I do a two-dimensional Fourier transformation with respect to T1 and T2, then you get a signal for each which is convoluted in the frequency domain. What is a convolution? So if people forgot what is a convolution, let me try to remind you about it. Maybe I can do it for the 1D. What is a convolution? So you have the Dirac delta function at plus omega I, which is frequency discrimination, and a convolution with respect to a Lorentzian line shape. Why does a Lorentzian line shape come up? It comes up due to the relaxation. Why did the delta function come up? That's because of the oscillation part. So what's a convolution? You take a point by point multiplication. So for this point, you end up multiplying all of the points together. Then for this point, you multiply all of the points together. So slowly, if you take point by point, when you end up reaching this point, you will have a point by point multiplication, which will nicely inscribe a resonance there. That's how you get a signal. Did that make sense? Yes? Similarly, here, we are just looking at two Dirac delta functions. So therefore, what does this mean? This just means this is going to give a resonance at omega I. And the S part is going to give a resonance at, let's say, plus omega S. These are two different dimensions. So here I'm talking about omega 2 dimension with respect to, let's say, proton, omega 1 dimension with respect to carbon 13. Somehow, if I have to generate this density matrix, which we'll see in 5 minutes, but let's assume that we have the capability to generate this density matrix. There's a multiplication in time domain. Therefore, it has to be a convolution of two Dirac delta functions and frequency domain. So let's see how it will look. The zeros being referenced here just to show the carrier frequency. You set the carrier frequency at a certain place. You agree these two Dirac delta functions are there? What is a convolution? You can literally take this point here, multiply with this point here. What do you get? 0. You guys realize that everywhere it will be 0, except for the place where you'll get a non-zero number there. Of course, I didn't put relaxation in. If you put relaxation in, you'll get a peak there. No, just not a delta function. Does that make sense? So provided we are able to generate the density matrix of this kind, then you do a two-dimensional Fourier transformation, one with respect to T1, the other with respect, one with respect to T2, the other with respect to T1. You get the respective resonances, and if they are convoluted, then you get a two-dimensional NMR peak. Yesterday, you are seeing such resonances in a two-dimensional spectrum. So now the question is how to generate the desired density matrix. That will be our question now, right? This we are very good at. Now you will see how many concepts you learned earlier. We are just going to apply very fast. The first 2D experiment that was proposed by James Jenner in the early 70s is called correlation spectroscopy. I think my spelling is wrong, but anyway, SY generally in NMR stands for spectroscopy. I'm not going to start with the cozy experiment due to other reasons. I'm going to start with a heteronuclear two-dimensional NMR experiment because it's very easy to understand that. Then we can go to homonuclear correlation experiments. Okay. The COSY experiment is a homonuclear correlation experiment. Basically, it correlates protons to protons or carbons to carbons and so on. Can also correlate heteronuclei, but very less commonly. So we'll start with an experiment which will correlate carbon to proton spins. The first experiment I'll end up taking is a less number of pulses experiment called the HMQC, heteronuclear multiple quantum coherence spectroscopy. Although we have seen SQC and MQC, why am I starting with MQC? Because this experiment has the least number of pulses, so it's very easy to understand what's going on. Okay, let's see how the pulse program looks. From here on, when I do something like this, it implies decoupling. Okay. And the two channels that you're trying to look at are proton and carbon. The first pulse that you end up applying is a 90-degree pulse on the proton. You start with the thermal equilibrium of proton. You apply a 90-degree X-phase pulse. You end up generating minus IY. You're talking about spin system where C13 is coupled with 1H. Therefore, they will have an active scalar coupling that's going to be present. So the Hamiltonian throughout this entire scheme is going to be given by omega H Hz plus omega C Cz plus pi J CH 2 Hz Cz. Why are we taking the weak coupling approximation here? Not just because we have done it throughout the course. The chemical shift difference of carbon and proton are so vast and your scalar coupling is so small, it's always in the weak coupling limit. That's why biomolecular NMR at times is easier to understand than small molecular NMR. In small molecular NMR, many times strong coupling comes in. Okay, so it's so much easier because the scalar coupling Hamiltonian will almost always only be the weak coupling Hamiltonian. Okay. So with this being the Hamiltonian, where you have chemical shift of proton, chemical shift of carbon, and the scalar coupling, we have to look at what kind of modules we are trying to optimize here. So let me tell you one thing, let me add a few labels in it that will make a little better sense. This will be a tau delay. This will be the remaining tau delay. While this will be a variable time delay of T1 and T2 is the direct dimension acquisition time. And the 180-degree pulse is carefully applied at T1 by 2. So this is the pulse program, which will generate the necessary density matrix. We will see as we go forward. The important thing that you see here, it's like a tau plus T1 by 2, 180-degree pulse, and T1 by 2 plus tau. This is similar to a tau prime, 180 tau prime. Therefore, what will not evolve? Of what? Good. So this tau prime, 180 tau prime will not allow the proton chemical shift to evolve throughout. Right? And until this part, since you're only going to have CZ component or no C component, carbon chemical shift will also not evolve in these tau durations. So during the first tau period, we realized that only pi j 2 HzCz will evolve. Proton will not evolve throughout this duration. Carbon will not evolve in these durations because you will see until this duration, you will either have CZ component only or no C component. So therefore, it will commute. So the first part, I'm just evolving it's a scalar coupling. So now this will be equal to minus Iy cos pi j tau plus 2Ix, sorry, I meant to I. Hz, Hy, Hy, Hx, Cz, sin pi j tau. And what is the main purpose of the experiment that we are trying to do? We are trying to transfer the polarization from proton to carbon. If you want to do that, only this has the carbon term, this does not have the carbon term. Can any of you tell me, therefore, what should you set tau to only ensure this component exists? Good. So tau should be set to 1/2j. And therefore, this part will go to 0. This part will remain 2hxcz. So basically, we have the density matrix as 2hxcz at this point. The next thing that happens here is that you have a 90-degree pulse only on the carbon channel. You are not applying anything on the proton. So only carbon will get affected. If you end up taking a pulse along the X phase, then you end up having HXCY, the negative sign. Alternatively, if you did it along the Y phase, they're going to have HXCX, irrespective of whichever it is. I'm sure you guys appreciate that this is a multiple quantum coherence term. Okay, so at this point, what have we generated? At this point, we are at 2hxCx, 90 along Y. Let's go back to the Hamiltonian and take a look at this. During this duration, what will happen? It's still at tau 180 tau, so proton chemical shift will still not evolve. And if you have multiple quantum coherence, will scalar coupling evolve? So scalar coupling will not evolve. On the other hand, now you have generated carbon coherence. Will carbon chemical shift evolve?
C. There is no 180-degree pulse in the C space.
You're right. There's no 180-degree pulse in C. That's one way of answering. What is a more straightforward way of answering?
This is a transverse component.
Good.
The transverse component.
Excellent. So one way of thinking about this is that it's transverse component. Since there is no 180, since it's transverse, it will have to evolve. But what makes you say transverse component should evolve? So you look asking whether this commutator is 0 or not. It is not 0. It's basically, if the density matrix is of this form, the Hamiltonian is of this form. This is time evolution Liouville von Neumann equation. So therefore, the only element that's going to evolve during the T1 period would be carbon chemical shift. So therefore, what you end up getting, 2hxCx cos omega c T1 plus 2hxCy sin omega c T1. So basically, during this entire duration, what is happening is that only carbon chemical shift is evolving. So therefore, whatever you started as a multiple quantum coherence still remains, and its orthogonal part comes up along with the cosine and sine modulation of the carbon chemical shift. So the next part that is going to be present is the 90-degree pulse on carbon. Which axis should be applied across? I would prefer to apply across Y because we have been following the first term. Let's continue to follow the first term. You can apply it along X also. You'll get some other transfer, but it's still fine. So you're going to get 2hxCz with a negative sign cos omega c T1 plus 2hxCy sin omega c T1. So with this being the case, this is the last pulse that we applied, and we only have a delay here, no more pulses on any of the channels. So only the single quantum term you need to take forward. Others will not be required. Out of these two terms, you see that this is a single quantum term, while this is a multiple quantum term, meaning that this will not be observable. So we should only care ourselves about this component. And what do we have at that stage? You have tau delay. Let's go back and ask, during this tau delay, what is the effective Hamiltonian? Already to start with, we said it's a tau prime 180 tau prime. So proton chemical shift will not evolve during this tau prime. We can ask whether carbon chemical shift will evolve. So will carbon chemical shift evolve for this term? Yes or no? Why? That's right. So you're checking commutator of CZ with HXCZ, which will be 0. And therefore, carbon chemical shift will also not evolve. Will scalar coupling, pi j 2 CZ HZ, will that evolve? Will scalar coupling evolve for this antiphase single quantum term, HXCZ? Will this commutator be 0 or non-zero? Non-zero. Tell me what is the value of this commutator?
Minus HYC.
Minus HY?
C.
Are you sure? So basically, you have a CZ on both. There'll be a CZ square, which is 1 over 4. You won't get anything except for minus HY. Go refresh your basics. So therefore, what is going to happen? I'm going to take cos omega C T1 out with a minus sign. So you're going to have 2 HX CZ cos pi j tau and then plus HY, because the 2 will get cancelled with CZ square, right? HY sine pi j tau. That is the only term that will exist, correct? This is the only term, because the other term can exist, but we cannot observe it anyway. And it will anyway not evolve with scalar coupling. It will remain as it is, and it's not going to be observable. You can literally write the same thing down here. So this is the term that you got. What did we set the tau to? Previously, you set the tau to something, and you cannot change it anymore. What did you set tau to? 1 by 2j. We have to keep it same, else the proton chemical shift will start evolving. So you can't change things halfway. 1 over 2j. 1 over 2j will kill this term. The only term that will exist is minus cos of omega C T1 HY. This is your density matrix before acquisition. Right? Did you guys slowly observe that you got the cos omega C T1 part? And when you end up acquiring the direct dimension, let's do the next step also, which is T2. In T2, what all are going to exist? You're going to have omega H HZ, omega C CZ, pi J HC, 2 HZ CZ. These are the terms that will exist. If you end up decoupling, this will not evolve. You are making sure that evolution is cancelled, nullified by decoupling. And you know for a fact that carbon chemical shift will not evolve because it's a proton operator that's being present. So carbon chemical shift will also not evolve. Right? So the only thing that's going to evolve is proton. So let's see what we get. Minus cos omega C T1 HY cos omega H T2 minus HX sine omega H T2. Okay. Therefore, what you are able to observe, of course, if you do a quadrature detection, this cos omega H T2 will become e power I omega H T2, right? So this is just one aspect of it. If you do quadrature detection, which I said you get both components, go back to the 1D NMR to understand how did you get this as your density matrix. Remind yourself, how did you get this? You only got cos then, but how did you go to e power I omega t at that point? That's the same thing we are doing here. If you end up doing a quadrature detection, what is quadrature detection? Get both cos and sine part. On T2, on proton channel, your density matrix at that point will be cos of omega C T1 times exp I omega H T2. Let's not be in a hurry. And let's only do one-dimensional Fourier transformation with respect to the T2 axis. What are you guys going to say? Oh, that's only going to give me a chemical shift of proton in the proton dimension. Okay. It's going to be modulated by the prefactor, which is cos of omega C T1. Let's take an example. Let's say your carbon is at the carrier. This will be 0. Cos of 0 is 1. So basically, you are not going to get any modulation if you carefully keep the carrier at the carbon itself. On the other hand, let's say this is non-zero. It can be positive or negative. It's going to be cos of minus theta is minus cos, is cos theta. Cos of minus theta is cos theta. So it doesn't matter whether you're positive or a negative offset. It's going to be the same. On the other hand, therefore, the T1 will modulate the intensity of the Dirac delta function now. Is that true? Let me repeat it again. You will get a Dirac delta function. If this did not exist, if this was 1, you would have gotten 1 at omega h. True? Now, on top of that, you have a multiplication of a cosine term. Let's assume a non-zero omega c. depending upon the value of T1 and the product of T1 with omega C, you will have a cos of something. Cos of something will range between 1 and -1. True? So therefore, if you are able to do this experiment such that for the first experiment that you're doing, the T1 is 0. Let's take T1 as 0 initially. You're only going to get omega of delta at omega h. Let's say you take T1 as a first dwell time. What is a dwell time? Remember, there is spectral width on both dimensions. If you have a spectral width for carbon, that will decide the dwell time 1. True? This is what we saw in the 1D NMR experiments. If you have a spectral width, it decides the dwell time. Let's assume that the first experiment, we set T1 to 0, small T1 to 0. You get the Dirac delta function at the chemical shift of the proton that you're looking at. Let's do another 1D experiment such that instead of keeping that small T1 to 0, you just increase it to the dwell time that is required. What you will realize is that this signal is going to get modulated. It's going to lose a little bit in intensity. Correct? You keep on doing this experiment where the next one is 2 times dwell time. Next experiment is 3 times dwell time. What is going to happen? This signal will get modulated based on this time delay that is being changed. True? Remember, you have a modulation. You already know the Dirac function, delta function, where it comes. You know the T1. Therefore, if you take the intensity, you will be able to get an oscillation from which you should be able to decipher the carbon chemical shift. It's a very indirect way I'm trying to make you understand how the signal comes in a 2D. But overall, did you guys understand how the delta function comes at T1? If yes, as you keep increasing the T1 time slowly, one increment at a time, every 1D experiment is just going to change the delta function as a sinusoidal wave, as a cosine of omega C T1, based on its directly attached carbon's chemical shift. Go back to this. If I have the handle of changing T1 carefully per experiment, I'm going to get the Dirac delta function at the chemical shift of the proton. You have all controllable variables. The only unknown is omega C. Therefore, if you keep changing T1 in various increments, you will be able to modulate the delta function as a based on cos of omega C T1, where T1 you set. Therefore, if you pick each of this modulation, pick the intensity, and if you know the certain T1, you'll be able to pick up what is cos of what is omega of C. That's essentially how a 2D experiment is done. 2D experiment is a sum of multiple 1D experiments, not a direct sum. You end up accruing multiple 1Ds to put together. There's one more component which I'm not told very clearly. Similar to acquiring the cos component, you should also acquire the sine component, because you want a complex Fourier transformation for frequency discrimination. You need a quadrature detection also in the indirect dimension. So now I hope I have driven the point what is indirect about it. You didn't, as you directly measure the chemical shift of proton just by turning on the receiver, here you are indirectly deciphering the carbon chemical shift, looking at the modulation of the proton signal. Let me repeat for the sake of understanding. Unlike the fact that the proton chemical shift was directly acquired by turning on a receiver, here the carbon shift is indirectly deciphered by looking at the modulation of the proton signal. So therefore, anything that you're modulating and getting its chemical shift will be called the indirect dimension. You don't directly see it, but you can indirectly deduce it. So these are the 2 dimensions in the experiment that we are trying to say. What I would request you guys to do is that the first experiment, we just did this as 90 degrees Y phase pulse. Go back, keep the exact same pulse program, just change the 90Y to 90X or 90 minus X, for instance. Change it to 90 minus X. You would repeat the entire process, and instead of getting cos, you will actually get the sine part. Go back and repeat the density matrix formalism. Change the phase of the first 90 pulse on the carbon from 90Y to 90 minus X. Instead of getting the cos modulation, you'll get the sine modulation. Therefore, if you get the cos and sine modulation, if you add them with orthogonal component, you'll be able to get the EXP I omega C T1. 13C 90 degree first pulse with minus x. And at that point, you will get sine of omega c t1 delta omega h minus omega 2. The moment you get these two, you would be able to generate by their combination the density matrix, which will be exp I omega c t1 exp I omega h t2, which when you two-dimensional Fourier transform will get a Dirac delta function at omega c and a Dirac delta function at omega h, which are convoluted with each other to get the 2D. Okay? Go back and think, solve it, understand. I'll share a wonderful review paper that talks a little more details of it. Read it during a week later. We'll talk also about another experiment called the heteronuclear single quantum coherence spectroscopy next class, which is HSQC that I was showing. The reason why I ended up choosing the HMQC is that it has the least number of pulses, just a few delays, and therefore people will be able to catch up the idea a little easier.